Welcome back to AI Codecast. Today, we're doing a deep dive into a pretty cool problem, the number of islands problem.
hmm
And it's a classic coding challenge, the kind that tech companies just love to ask during interviews. So get ready to flex those algorithm muscles.
Absolutely. This problem really gets you thinking outside the box. Like, how do you efficiently find your way through data?
Okay, so imagine a map, right? But instead of mountains and rivers and all that, it's all ones and zeros. So ones are land, zeros are water. Your challenge is to figure out just how many separate islands are on this map.
The key here is how we define an island. It's like, imagine you're sailing around this map. An island is any piece of land you can reach without, well, getting wet, right?
No swimming allowed.
Exactly.
Yeah.
So land connected horizontally or vertically all counts as one island, but if it's diagonal, well, you'd need a boat.
Right, like a real archipelago.
Exactly. Now, let's say we have this grid, listeners. Picture this with me. A top row of four ones, then below that, two ones, a zero, and another one. The next row has two more ones, and then all zeros, and the last row is all zeros.
Okay, I'm trying to picture this. So how many islands do we have here?
Just one. Yeah, even though the land's kind of in a weird shape, it's all connected horizontally or vertically.
Got it. So it's not about the size of the landmass, but whether you can walk from any point on it to any other point without getting your shoes wet.
Now, how would you go about counting these islands with code? What's your first instinct?
Well, I guess my first thought is to just go through the grid cell by cell. Every time I find a one, I'd check if it's connected to any other ones nearby.
That's basically the brute force approach, systematically going through everything. And it's a natural starting point for sure. But as you start doing this, you'll probably run into a problem. What happens when you find a big island?
Oh, I see. With my approach, I might end up counting the same island a bunch of times because I'd be hitting different ones that are all part of the same landmass.
Exactly. And that's where brute force gets inefficient. We're doing the same work over and over, checking cells we've already been to. So how do we avoid that? Any ideas?
Well, maybe we could keep track of which cells we've already visited, like leaving a trail of breadcrumbs so we don't go in circles.
That's a great analogy. And that's exactly what smarter algorithms like depth-first search or DFS do. They're like explorers who never waste a step, making sure we count each island only once.
Okay, so DFS is all about efficiency. Tell me more about how it works.
Imagine you're in a maze. DFS is like taking one path as far as it goes, even if it leads to a dead end. Then you backtrack and try another path, and you keep doing that until you've explored every nook and cranny.
So how does that apply to our island problem?
Well, we start at a land cell, mark it as visited, and then use DFS to explore all the land connected to it. It's like following that maze path. We keep marking cells as visited as we go, so we don't accidentally count them twice.
That makes sense. So if we hit water or the edge of the grid, we know we've hit a dead end and we backtrack.
Exactly. We repeat this for every new unvisited piece of land we find. Now, here's where it gets clever. Instead of making a separate list to keep track of visited cells, which takes up more memory, we can actually just change the grid itself.
Wait, wouldn't changing the grid mess up our original map?
Good question. It wouldn't, because all we care about is whether a cell has been visited. So as we explore, we can change the ones of visited land cells to something else, say a 2.
Ah, so that's how we avoid getting stuck and save space. That's clever. So how do we actually write DFS? Do we just do a bunch of if statements?
Not exactly. DFS uses something called recursion, where a function calls itself. It's like those Russian nesting dolls.
Okay, how does recursion help us count islands?
So picture this. We have a function, right? And it takes the location of a cell as input. It first checks if the cell is land, if it's within the grid, and if it hasn't been visited. If all those check out, we mark it as visited. And then, here's the recursion part. We call that same function for each of its neighbors.
So each neighbor triggers another check, and that triggers more checks and so on.
Yeah, it's like a chain reaction of exploration. And this chain only stops when we hit water, the edge of the grid, or a cell we've already been to. This makes sure we thoroughly explore every bit of an island before moving on.
So are we ready to move on to part 2 of this deep dive? Because I think our listeners could use a moment to digest all this recursion magic before we jump into more solutions.
Great idea. We'll be back soon with even more clever ways to tackle this number of islands problem. Welcome back to AI Codecast.
Where we're still exploring the number of islands problem,
We've seen how depth-first search can help us count those digital islands.
which let me tell you is already pretty mind-blowing with all that recursion stuff.
It's a powerful tool, for sure, but there's another approach that's just as clever, and it's also often used for this kind of problem, breadth-first search, or BFS for short.
BFS. Okay. I'm getting some, like, search and rescue vibes from these algorithm names.
Haha. Yeah, I see that. Imagine you're like coordinating a search party, right? DFS is like sending out one explorer to follow a single path as far as it goes. BFS is more like deploying a whole team, fanning out in a systematic way.
So instead of going deep, we're going wide.
You got it. Think of it like ripples spreading out from a stone dropped in water. BFS explores the grid layer by layer, visiting all the cells at a given distance from the starting point before moving on to cells further away.
So first we check all the cells right around our starting land cell, then the cells one step further out, and so on.
Exactly. And this layered exploration is actually super useful for finding the shortest path between 2 points.
I didn't think about that.
Yeah.
So while DFS is great for exploring every single corner of an island, BFS could tell us like the fastest way to get from one side to the other.
Exactly. Now, how would we use BFS for our island counting problem?
Well, if we start on a land cell, we could use BFS to explore all the connected land, going layer by layer, just like those ripples you mentioned.
That's the right idea. And just like with DFS, we need a way to remember which cells we've already visited so we don't count the same island over and over again.
Right, we don't want our search party getting lost and going in circles. So we'd still mark cells as visited as we explore them. Could we also modify the grid itself with BFS, like we did with DFS?
Absolutely. We can use the same trick here. Change the values of visited land cells so they stand out from the unvisited ones.
Okay, so that part's similar. But how do we actually do this layer-by-layer exploration? Recursion doesn't seem like the right tool for this, does it?
You're right. Recursion isn't the best fit for BFS. Instead, we use a different data structure, something called a queue.
A queue, like waiting in line for something.
Exactly. Think of it like this. We add our starting land cell to the queue. Then we take the first cell from the queue, explore its neighbors, and add any unvisited land neighbors to the back of the queue.
So it's like our search party keeps getting new instructions. Okay, we've checked this cell, now go check these other ones.
That's a great way to put it. And we keep doing this until the queue is empty, which means we've explored all the reachable land cells from where we started.
Sounds pretty systematic.
Uh.
So with both DFS and BFS, we're basically exploring the whole island connected to our starting cell. Is there ever a reason to pick one over the other for this problem?
That's a great question. They both work well for counting islands, but they do have some subtle differences. DFS, with its depth-first nature, often feels a bit more intuitive for this kind of exploration. It's like following a single thread until it unravels completely.
But you mentioned BFS is better for finding the shortest path. Does that ever come up in this number of islands problem?
It could. Imagine you need to not only count the islands, but also find the most efficient way to connect 2 points on an island, like maybe for building a bridge or something. BFS would be the way to go for that.
Ah, so it's like having different tools in your coding toolkit.
Yeah.
You choose the one that's best for the job, right?
Exactly. Now, apart from how they're used, there's another subtle difference between DFS and BFS, especially when you have really big grids. Any guesses?
Well, DFS uses that recursion thing, which I know can sometimes cause problems if you have too many nested calls. Is that what you mean?
You got it. For really deep explorations, DFS can run into something called stack overflow, where the computer's memory basically gets overloaded with all those function calls. BFS, with its queue-based approach, tends to be more reliable in those situations.
So BFS is a bit gentler on memory for huge exploration tasks.
You could say that. But of course, both algorithms have their strengths and weaknesses, and the best choice often depends on the details of the problem and what's most important to you.
That makes sense. So we've covered brute force, DFS, and BFS. Are there any other cool ways to count islands that we haven't talked about yet?
There is one more, and it's a bit of a wild card. It's called union find.
Ooh, a new challenger. Tell me more.
Union find is a really interesting data structure that's specifically designed for managing connected components, and you guessed it, it's perfect for our island problem.
So how does it work? Is it like DFS and BFS where we go through the grid and mark cells?
It's totally different. Imagine each land cell is its own little kingdom, right?
Yeah.
As we explore the grid, we use the union find algorithm to merge kingdoms that are right next to each other, forming bigger and bigger empires.
So if two land cells are touching, they become part of the same kingdom.
Exactly. And we keep merging kingdoms until we've looked at the entire grid. In the end, the number of kingdoms we have left is the number of islands.
That's a cool way to think about it. It's like a game of Risk where players keep taking over neighboring territories. So is Union Fine like the ultimate island counting champion?
It can be incredibly efficient, especially for problems where the connections between components are constantly changing, but it's also a bit more complex to understand and use than DFS and BFS.
Well, that sounds like a challenge for our AI Codecast listeners. Maybe we could do a whole deep dive episode just on Union Find sometime.
That's a great idea. It's a really powerful data structure that has a lot of uses beyond just counting islands.
I can already see a future episode happening. But for now, let's get back to our current island adventure. We've talked about a lot, from brute force to the magic of recursion and the systematic approach of BFS. What's next?
I think it's time to make things a bit more interesting. What if our islands weren't static? What if they were constantly changing like real coastlines that are shaped by tides and currents?
Ooh, that adds a whole new level of complexity.
Right.
Our algorithms would need to be able to adapt to a changing environment.
Exactly. So before we wrap up this deep dive, let's try and figure out how to handle that. Imagine a real-time map of an archipelago where the ones and zeros are always changing. Which of the algorithms we discussed would be best at keeping track of the number of islands in this ever-changing landscape? That's the question we'll be exploring in our final part.
Welcome back to AI Codecast.
We're back for the final part of our deep dive.
And it's time to really put our island counting skills to the test, right?
Exactly. We've looked at some pretty smart algorithms, but now we're going to up the challenge.
We're talking dynamic islands now. So it's like our grid of ones and zeros is constantly changing, like a real-time map of a coastline or something.
Exactly. No more static pictures. It's all shifting sands now.
So the land and water cells are like updating all the time, maybe from sensor data or some simulation.
Right, which means our algorithms need to be super adaptable and efficient to keep up.
This is where it gets really interesting. So let's go back to each approach and see how it would handle this kind of dynamic situation.
Sounds good.
Okay, so let's start with the simplest one, brute force. Could it even handle this kind of constant change?
Brute force would really struggle here, because every time the grid changes, even a tiny bit, we'd have to scan the whole map again from the beginning.
And that sounds super inefficient.
Yeah, it would be, especially with large grids or frequent updates. We'd be constantly redoing the same work over and over, checking cells that haven't even changed.
Right, so brute force is out. What about depth-first search? Could we tweak it for this dynamic challenge?
It could potentially work, but we'd need to make some smart changes.
Like what?
Well, we'd need a way to quickly figure out which parts of the grid have actually changed and only rerun the DFS search on those specific areas.
So instead of starting from scratch every time, we'd focus our efforts.
Right. But to do that, we'd need to keep track of which cells have switched from land to water or vice versa.
And then use that information to guide our DFS search.
Exactly. We'd have to choose where we start our DFS dives based on where the changes happened.
That sounds like it could get pretty complicated to program.
Yeah, it would definitely add some complexity. But it's totally doable with some clever tracking and some tweaks to the algorithm.
Okay, so DFS could work, but it wouldn't be simple.
Yeah.
What about breadth-first search? How would it handle a map that's constantly changing?
BFS might actually be a better fit for this dynamic situation.
Oh, really? Why is that?
Because of its layer-by-layer exploration style, it's really well suited for these incremental updates.
I see what you mean. Instead of exploring a whole island from a single starting point, we could just start a BFS search from each cell that's changed.
Exactly. And we'd only need to search outwards from those changed cells until we hit either the edges of the grid or cells we've already visited.
So we basically be updating our understanding of the islands in a more localized way, right?
Exactly. This would help us avoid re-exploring big chunks of the grid that don't need it, making it much more efficient than a full DFS or brute force approach.
So BFS seems like a good candidate for these dynamic islands.
Definitely. It's worth considering for sure, but the best choice always depends on the specific problem.
Right, like how often the grid changes, how big the changes are, and all that.
Exactly. And now for our last one, Union Fine. What do you think about how this approach would handle a dynamic environment?
That's a tough one. Union Find is great at managing connected components, but I'm not sure how well it would deal with cells constantly flipping between land and water.
Yeah, the real brain teaser. We'd need to figure out how to efficiently update the Union Find structure as those changes happen.
Like if a land cell turns into water, we'd have to break up its kingdom, which might create new ones.
And if two separate islands merge because of a change, we'd need to combine their kingdoms.
It sounds like Union Find could work, but it would require some really creative thinking and careful coding.
For sure, it would be a fun challenge, but that's what makes algorithm design so cool, right?
I agree. It's all about finding the most elegant and efficient solutions, even when the problem throws us a curveball like dynamic islands.
Well said. I think we've covered a ton of ground today.
Yeah, we went from the basics of exploration to some pretty advanced algorithms and even tackled how to deal with dynamic systems.
It's been a real deep dive into the number of islands problem.
We hope you enjoyed this episode of AI Codecast.
And that you're feeling inspired to try out some algorithmic challenges yourself.
So until next time, happy coding, everyone, and may all your islands be optimized, static, or dynamic.